And so here you just move this molecule one position, didn't get any results from that. Then you pull off a water molecule. See, that's what this did, set up the next reaction. The next reaction, there's an enzyme that pulls out a water molecule, and there you've seen this before. Here's a P double bond O joins with an oxygen, a C double bond C. An O between two molecules with double bonds like that is that double acid. And so PEP is a double acid, and this is a most unusual acid. It's the only place, I'm sure it exists someplace else, but this is the only example I know of it. And so you get a very powerful double acid here that does have the energy to transfer that phosphate that you move to the second position to ADP to make ATP. And since we've been working with two molecules ever since we split glucose, you finally come out two molecules ahead. And of course, this is a kinase enzyme that does that reaction. Whew! Okay. And so now you've actually gained some energy. And this is the energy gain in glycolysis or fermentation. And this is energy harvest without oxygen, anaerobic respiration. And then you wind up with, when that molecule adds the phosphate to ADP, you've got this molecule temporarily that automatically shifts position to become this molecule here. And so pyruvic acid, and this would be the regular formula for it, looks like that. It's one of the most valuable molecules in the living cell. There are a lot of diagrams and biochemistry books that have pyruvic acid here, and then the arrows going off in 7, 8, 10 different directions, and all the molecules that can change into and that can be changed into it like that. Okay, so now we managed to split glucose. We had to spin 2 ATPs to get it activated. Now we've snuck a little extra phosphate on there and used the energy of these enzymes and anticipation and complex prerequisites to get down to pyruvic acid. We're almost done. Okay, we are done with energy harvest. That's all the energy you get out of this is 2 molecules of ATP. But there's one more thing you need to do. Recycle the prerequisites. Okay, and so here's the pyruvic acid that we just had. But notice, now the ATP is going to get spent, making muscles work and nerves work and producing hormones and making, enzymes work in living cells and all the other life functions. Or the ATP is going to get used up. It'll be converted to ADP. That'll go back and get another phosphate and become ATP and do something. So you know where that's being recycled. But what about the NAD? This little hero where I wrote the word complex prerequisite, where did it come from? And the process isn't going to go anywhere. That's what you needed to make the extra ATP down here. If you don't have this right here, then this phosphate sneak didn't get you anywhere. Without this complex prerequisite, the nicotinamide adenine dinucleotide, you can't go to this step. You can't even break even as far as energy is concerned. So this reaction comes to a grinding halt unless there's some way to take the NADH2, the one that picked up the 2 hydrogens, and change it back to regular NAD. And so you got to recycle the prerequisites to keep the reaction going. Well, here's pyruvic acid, and there's 2 ways to get the NAD back. In our muscles, and the muscles of animals in general, the hydrogens picked up by NAD in that step that made the first ATP energy break-even point, if you hand them directly back to pyruvic acid, they wind up on the second carbon, and you get lactic acid. Well, here's a good illustration of a little knowledge is a dangerous thing. Now, many of you have heard of lactic acid, and they're lactic acid bacteria, and they're lactobacillus, is a bacterium people like to have in their intestines and all. And lactic acid is a chemical that builds up in heavy exercise. When you're really exercising a lot and you're using up more energy, you're not taking in enough oxygen, to break the sugar down all the way. You build up, quote, an oxygen debt. And so you got a lot of lactic acid that later on, oxygen can finish burning it and give you the rest of the energy. But meantime, you've got this lactic acid building up in your bloodstream. What does that do for you? Well, the thing it's supposed to do for you, the thing it was designed to do for you, is to make you feel tired. Okay, and so when you're beginning to get lactic acid build up in the bloodstream, that's the body's way of telling you, hey, you're burning energy faster than you're taking in oxygen, slow down or die, okay? All right, well now you get somebody, you know, with a little bit of background in biochemistry, swimming, okay? So, oh, this is just terrible. But this was in Pennsylvania, so I didn't get to swim all year round. But so when a pool became suitable for swimming, I just always liked swimming underwater. And so I'd swim underwater, and I'd go the length of the pool. And my goal was to get up to going down the length of the pool and back, you know, in one breath. And so, you know, first I was doing good to make it down, and I'd make it down and turn, and I'd make it down and get maybe halfway back, and 1 3/4 way back. And then one day, I thought this was it. Okay, so I swam underwater, you know, I made it all the way down there, a good turn, heading back, you know, past my old mark, and I tried to breathe out. You want to breathe out carbon dioxide while you're doing this, because carbon dioxide is a breathing stimulus that's telling you, hey, nut, you're running out of air. Come up and breathe, you know. But see, if you know these things, I knew that my muscles still worked, okay, and it was only lactic acid telling me that, you know, I was running short on oxygen, but I knew my muscles still worked. And so I tried to breathe out a little more CO2, couldn't. I was all out of breath. Okay, but I could see the end of the pool. And I got this lactic acid stimulus. It was, you know, a bit painful and annoying, but I knew my muscles still worked. This was just a signal. And it was only that far. And so I made those last few strokes and, you know, threw myself up on shore like some beached whale, and proud of myself until every muscle in my body began to ache. I am not sure how long I just laid at the end of the pool, you know, trying to pay back this oxygen debt. You know, and then I'm supposed to go to class to teach. You know, none of my muscles work. You know, Charlie horse in every arm, every leg, every rib muscle. And for about 3 days. Okay, someday I'll tell you my hypothermia story, but not today. But so don't ignore that stimulus. When lactic acid is telling you enough is enough, when you breathe out your last CO2, okay, you're close to death, quit. Okay. God had you in mind. He wants you to come up and, okay. But at any rate, that's what happened to us. We just make lactic acid out of it. And then in aerobic organisms, one that can burn this with air will eventually get a lot more energy out of that. Well, yeast do something slightly different. We have one enzyme. It's just lactic dehydrogenase. It just adds the hydrogens from NADH2 and makes lactic acid. Well,